So last time, what were we talking about?
Band steepness.
Band structure of a 1D hydrogen chain.
Yeah, a 1D hydrogen chain is what we got to last time. Your assignment, which I wanted you guys to work on but didn't post soon enough, had to deal with plotting lithium. So you guys are going to do that for your next classroom assignment. You might have an additional one on top of it. But last time we were talking about, like, why do the bands run? So far in the 1D hydrogen chain, we've drawn the band structure of it. What was the x-axis? What was its label?
K.
Yep, K. And then remember, it was a vector. And do you remember what did K keep track of, or like what is K?
It's based off of de Broglie, right? It measures momentum.
Yep, it measures momentum as you travel through a crystal. What else does it keep track of?
Counts the nodes.
Yep, counts the nodes. Yep, that's a big one. And basically what it is, if you boil it down, it's talking about symmetry. So it's the symmetry of the molecular orbitals that we're looking at. Do you remember what were the limits that we went to?
0 and pi over A.
Yeah. And what was A again?
A was in angstroms. It was the length.
Yep, it was the length. What was that, Tara?
Wasn't it the length between those?
Yep,
Length of the unit cell.
Yeah, it's the unit cell, or the length between the H atoms. It's going to get a little more complicated when we go to two-dimensional systems. What about the y-axis? What was its label?
Energy.
Yeah. Okay. And do you remember what this curve looked like?
It was a straight line, and it was the Fermi level.
Yep. So we do the Fermi level. We'll indicate that. And what's the Fermi level tell us?
The separation between occupied and unoccupied states.
Yep. It's also its true definition is the zero of chemical potential, but a way to think about it is all the states below that level are occupied, everything above it is unoccupied. Okay, what about, like, we've yet to actually draw the band structure. We've done everything else associated with it. What else do we need? Or what does this curve look like?
It's just the Fermi level.
It's like a extended.
That's what it's going to be.
I don't really know how to describe it.
It's like a hyperbolic tangent.
Yeah. Sinusoidal is, I think, what that's called. And it's cut in half. Why is it in half for the 1D hydrogen chain? So why does the Fermi level come up halfway?
Because that represents the energy of, like, the first electron, right? Or the only electron.
Yep. So there's only one electron in this system, and how many electrons can each band hold?
Two.
Two. Perfect.
Is this looking at when A is equal to 1?
Yeah, when A is equal to 1, we'll
okay.
say. At the optimal bond length. Yeah, because I think what you were thinking of, Maddie, was when it was at 3, and it was like a straight line, essentially.
Yeah.
Yep. Okay. So, yeah, but this is at the optimal bond length. But now, what about other systems? We want to go beyond the 1D hydrogen chain. That's way too simple. Let's get a little more complex today. So the next section is titled, How Do the Bands Run? Morning. How do the bands run? In order to do that, we have to look at the block functions. So we need to consider block functions. But these block functions themselves, they do not describe energy. So if you remember that psi sub k, that was equal to a summation. And you remember what else came after that?
Is it
Isn't
CN?
it Cn times x of n?
Yep, we got an X. Yep, the last term is X of N. We had an E. And what was that E?
IAKN.
Yep, I, K,
I can do something like
N,
that.
A. Yep. I know, man. Is that what I, K, N? I know.
I can, yeah.
I don't know. We'll go with it. I'm gonna make something to have me be the next YouTube sensation.
Oh,
So remember where N was just was the index that we had. K was the wave vector we chose, and N is whatever atom we're considering or basis function. Okay, so let's consider a 1D chain of px orbitals. So a one-dimensional chain of px orbitals. And we're going to look at that at k is equal to 0 and k is equal to pi over a. All right. So psi of 0, if you remember that this function changes a little bit, you're going to get e to the 0. So what happens to this first term?
becomes 1.
Yep,
Or
it
it
becomes
becomes
1.
X to the
Yeah.
1.
So we're left over with 1 to the n x sub n, right? So if we were to write that out, let's write that out for the first couple of terms. Give me some first couple of terms.
Chi0,
Yep.
Chi1, plus Chi2, plus Chi3.
Okay, great, and it continues on, right? Okay, now let's try to represent that. Like, what does that physically look like? And remember, the plus indicates if we've had a sign change or not. So let's say our first atom has a p orbital that looks like this. This is Chi0. Then we're going to have Chi1 here. What's it going to look like?
Filled in and then non-shaded.
So remember, we're not changing sign across here.
Yeah, but wouldn't you not, to make it the way it would be, yeah, make it so it doesn't change? Or are you saying as a whole?
As
it would
a
just have to
whole,
keep being the same. Okay, so yeah, it would just be the same as before then.
yep. Because there's a positive here, so that means there's no sign change between the atomic orbitals. Chi1, what's Chi2 going to look like?
The same thing.
Yep. And Chi3?
The same thing.
Yeah.
Killing it.
Nailed it. Okay.
Someone drank their coffee this morning.
Yeah.
I don't know. I'm actually just feeling awake. Or are you talking about Natty?
Oh.
All right, so now looking at this, these orbitals, they're all out of phase with one another. What does that mean for the type of orbital we're looking at?
The
Crystal
antibond.
orbital.
And
Yeah, we got an
antibond.
antibond. And what does that mean for the energy? Is that like high or low in energy?
Pretty high.
Yep. Okay.
Low.
Now let's consider when we're at pi over a for k. We get the same thing. Do you remember what happens to this first part? Oops, not showing it. This first part of the expression. How does that simplify?
E equals I pi n.
Yep. And that is true, but it
Or
ends
I mean,
up simplifying.
pi s, yeah, E equals.
It ends up
But there's the
simplifying.
-1 sign up front.
Yep, exactly. It ends up simplifying to that, right? Okay, so now let's look at what the block function looks like for that system. So we're going to start with our first orbital. Oh, actually, before we do that, let's write out a couple of these terms. What are we going to get in that first term? Geez, my camera's spazzing.
X sub 0.
Yep. X sub 0.
Minus x of 1
Yep.
plus
Next.
x of 2 minus x of 3.
Yep. And so on. Use that way. Okay, so now for chi1, what's that atomic orbital going to look like?
It facing the other way.
Yes. So should I shade in this side?
No.
Right. Goes on that side. And then, so there's a minus sign, then there's a plus sign, chi sub 2. What should this one look like?
It should be
The same as the first one.
Yep. And chi sub 3?
The same as the second.
Yep. Keeping with that repeat pattern. All right, now looking at this, are we going to have constructive or destructive interference between chi 0 and chi 1?
destructive.
Yep, constructive. So what does that mean? What type of orbital do we have?
Non-bonding.
Anti-bonding.
Well,
you
remember,
call it a
anti-bonding is where they're completely out of phase with one another.
No, so it's bonding.
Yep, this one's a bonding. And what is that going to be, high in energy or low in energy?
It's going to be our energy minimum.
Yep. Okay, now let's think of the type of overlap we're having here. How many regions of overlap are we having between these two orbitals?
Sigma. Like
Yep,
that's
sigma.
what I'm for.
So this is going to be a bonding sigma, and this is going to be an anti-bonding sigma, sigma star. Okay, everybody comfortable with that?
So why for that third term where technically it's going to be minus, or wait a second, no, that pattern does hold, never mind. Oh, yeah, wait, I'm sorry. So between the second, third term where it's
Mhm.
plus, why does it flip though? Because is it always just going to be in relation to the first term?
Yes, and if we put, so in this case, if we put a 3 in here, -1 to the third just ends up being -1.
Mhm.
Yep. So
But I'm
mathematically,
sorry, like by third term, I'm saying x sub 2.
oh, okay. So this,
Because like technically it's third term, but yeah, why does that not stay the same? Is it always going to be in relation to the first term?
yes, because if we
Okay.
have -1 squared in that case, so we get a +1. So it's really
Mhm.
more about the mathematics at that point. We will get to a point where these start flipping, like as we go through k-space. We're really talking about changing the symmetry as we go through that orbital. So like, for example, we'll see in a bit, one of these points might actually be flipped, and that's going to change the energy. So when we're talking about like, when we're talking about this, we could plot like the functions here, and they might be like in and out of phase every third or fourth one, like you were saying. Does that make sense?
Well, it's just more of that for that x sub 2, I would have figured it would be the same as x sub 1 since there's no sign change. Or
Oh, you
since
mean-
it's like plus.
Oh, yeah, plus, yeah, it's in relation to this guy.
Okay.
Any other questions? Okay, let's plot this bad boy. So if we plot, leave that. If we plot this, we're going to do the same range again. we're going to go, we have K along here, E along here. What are my limits again for the first Boolean zone?
0 to pi over A.
Yep, 0 to pi over A. All right, and last time, when we were looking at a 1D hydrogen chain, it looked like this, right?
Yeah.
Where were the bonding states? Like, if you had to pick a value of K that was most bonding, what would it be?
The ones underneath the EF.
Yep, that's true. Those are all bonding. Which one's the most bonding, though?
Is it at what pi 2?
Is it at 0?
2A.
Yep, it's at 0 where it'd be the most bonding. What about the most anti-bonding?
At pi over A.
Yep, exactly. Now we want to consider our p orbitals. What's it going to look like for this system?
It'll be the opposite because we're starting with anti-bonding and then running to bonding.
Yep, exactly. It's going to be the exact opposite. We're not going to indicate the Fermi level yet because we're just saying we have pz orbitals and they don't have electrons right now. So perfect. The important point is it runs the other way compared to the s orbitals. Okay. Well, how many p orbitals do we have per energy level?
2.
Nope, not 2.
Oh, 1.
Nope, not 1.
Never mind.
You're close. One more.
0.
3. So we have 2 more that we need to talk about, right? So what about
I'm so bad at this.
it's distance learning. It's tough.
I hate it.
I hear you. I miss your guys' banter in person. It's way better.
It's harder to roast through a screen.
Yeah, it really is. Sometimes you can't even hear it.
Can you move the paper up a little bit?
Oh yeah, like this.
Just so I can see that little top blurb.
Oh, I'm sorry.
Yeah.
There we go.
Okay, thank you.
Yep. Okay, so now we're going to plot the py and the px. We want to consider those block functions still. So at k is equal to 0, we get psi sub 0. And we already said what that block function is going to look like. Psi 0 plus psi 1 plus psi 2, and so on. So let's go to plot that. Remember, the py and the pz are going to sort of mirror each other because they're not pointing directly at one another. One's pointing up and down like this. The other one, which we'll worry about later, is pointing out at us, and it's difficult to draw. So we're just going to talk about these ones now because they're just easier to draw. Okay. All right. So now this is chi sub 0. What's chi sub 1 going to look like?
Same thing.
Yep, same thing. Chi sub 2.
Same thing.
Yep. Chi sub 3.
Same thing again.
Yep. All right. As these guys, they're in phase with one another all throughout. What type of orbital is this?
It's a pi.
Yep, it's a pi because it's overlap in 2 regions. And is it bonding or is it anti-bonding or non-bonding?
Bonding.
Yep. Okay, so remember last time we talked about bond dispersion, where quality of overlap determines how steep this band structure is. Just keep that in mind in a little bit. Okay, next, let's look at the other situation. Pi over A. In that case, oops, joke. We'll switch to red. Ooh. Feeling fancy. Okay. Let's plot that. Chi sub 0. What's chi sub 1 going to look like?
Opposite.
I'm sorry, Maddie, I didn't hear you.
I didn't say anything.
The top
okay.
is colored in.
What did you say, Tara?
The top is colored in.
Yep. Yep, we're switching phase. And how did you know that the top was colored in?
Because it's a minus.
Yep, exactly. So we're switching signs. There's actually a node that cuts right through there. All right, what about for chi 2?
The bottom,
Yep. Chi 3?
the top.
Yep.
Doctor.
All right, and what type of orbital is this one then?
Pi anti-bonding.
Pi
Yep.
star.
Yep, pi star. Anti-bond. Okay. So now, if we plot, let's plot the PY and the PX band structure, or excuse me, PY and PZ band structure. Oh. So plotting the PY and PZ band structure. Let's investigate on what it looks like. Am I okay to move this up?
Yeah.
So again, we have those exact same limits that we've done a million times. Pi over A, E. Okay. What's the band structure going to look like? Keep in mind, this is how our last p orbital looked. And this is how our s orbitals look. So what do you think? What's it going to look like? Are we going to start low and go high, or start high and go low?
Start low and go high.
Yep. Okay. Now, how many bands do I need to draw?
3.
Yeah, we will get to 3 because we're going to draw all 3 of them. But right now we're plotting the P, Y, and the PZ. So how many bands should I have drawn?
Two.
Yep, should have had 2. So let's say this is the PY. Then where's the PZ going to be?
Is it facing the other way, like starts high, goes low?
Nope, that's actually going to be the PX.
Never.
Yep, the one that we looked at that had sigma type overlap. We'll get there in a second.
Isn't
What
this whole
about-
diagram representative of PY though?
Right now it's just PY, but we need PZ in there too.
But they should
Did
lay
you say they're like the same?
on top of each other, right? Because
Yep.
they're both at the same energy.
Yep, Morgan and Josh, you're exactly right. They're on top of one another. Oops. And the PZ is also in there. We just can't see it because they're energetically equivalent. What do we call energetically equivalent orbitals?
Degenerate.
Yep, they're degenerate. Okay. So now let's plot everything on one plot now. Plotting all the p orbitals. I'm gonna do dashes this time, change it up a little bit. Pi over A, 0. Okay, and we have E. All right. So now the first thing we want to do is we want to consider the type of overlap. So the px orbitals. What type of overlap do they have? Like what type of orbitals are they? Or what type of crystal orbitals will they result in?
Sigma.
Yep. Or sigma. And the P, Y, and PZ, what were they?
Pi.
Yeah, pi. Okay. What does that mean about the dispersion? And what do we mean by band dispersion again?
The height of the band.
Yeah. Yeah, so the height of the band, how much does it move up? How much does it go down? So which one's going to have a greater amount of dispersion? The Py and Pz orbitals or the Px orbitals? Or if we were thinking about like a classical MO diagram, you have a sigma,
So the sigma would be bigger, so px.
one. So Maddie, or excuse me, Tara, you're right.
He doesn't even know our names anymore.
I know. I haven't seen you guys in so long. I don't know what to do.
Crazy.
So tough. I'm losing my sight too. I'm like, I've been stuck inside all day. So which of these MO diagrams would you expect? The one on the left or the one on the right? For a generic molecular system.
Left.
We got one vote. What'd you say, Josh? You said left?
Yeah.
Yeah. Any other votes?
Left.
Left?
How
Unanimous?
many be different? Challenge me.
All right, right.
It's the one on the left. Yeah. Unless we have really strong mixing, right? Okay. So, Tara, you said which one's going to have a greater amount of dispersion?
Sigma, so pi
Yeah.
x.
Greater dispersion. Pi is less dispersion. Okay. So now, let's say I draw my my px orbitals. In which way should they run? Should they go from high to low or low to high for the px?
High to low.
Yep, high to low. Let's say I draw it that way. So this is the px. What should my py and pz look like?
The other way.
Yep, but should the top and the bottom match this guy?
No,
No, what should happen?
it should be a little bit less.
Yeah. And that's what happens. They cross at about the same point. Py and the pz. So that's what it looks like. So note that the dispersion is less for these guys because they have pi overlap, where this px has sigma overlap. So it's going to have a greater amount of dispersion. Okay. Okay, let's move on to d orbitals then. Any questions about this, or everybody feel good?
I have a quick question. So if you were to plot all the p orbitals as one band,
Yes.
would look like the PX and PZ, but with less dispersion because the
Mhm.
PX would cancel out some of it? Or
Could you repeat the question?
if you were to plot all the p orbitals as
Yes.
a combined band, what would your final band would look like?
Oh, so it should look like this, like if you're plotting all of them. So you will get, it'll look like two bands, but there are actually three bands in there. Does that make sense?
Okay.
Did that answer your question?
My question is more, let's say we're ignoring the separate orbitals, the PZ, PY, PX, and we just draw all the p orbitals as one band. Could you do that or no?
No, they would result in two different bands.
Okay.
Yeah, just because of their symmetries and the type of overlap they have. They, depending on the crystal you have, you could have it, they could all be represented with one band, but for our system, you would get this image out or this band structure. Yeah, symmetries make a big deal with it though.
Thank you.
Yep. Okay, so let's talk about the D bands then. Am I okay to move this out of the way?
Yeah.
Well, so what about the D bands? Okay. How are we doing on time? We're okay, we got lots done. All right, so what we're going to do is we're going to assume we have a chain of a D8 atom. Let's go with platinum. So let us assume we have a chain of D8, I don't know, platinum complexes. The reason we're choosing a D8 system, D8 systems for the most, a significant number of them are square planar, and that'll help us look at this system. I know Josh is really interested in this platine, excuse me, for his independent research proposal. So,
Way to go, Josh.
Great. Yeah.
yeah. Okay, and we're going to space them out. They're infinitely long in space at a distance of A. So they're A apart. So if we try to draw this, this is the chain. I don't know, we're going to say this is the Z direction. I know you guys hate changing coordinate axis, but we're going to have this one be the Z. You'll see why. And we have two ligands that are pointing out, or up and down, excuse me. We have one pointing out towards us, and we have one going back into the plane of the paper. We haven't gotten to the point yet of talking about complexes and what happens to the d orbitals as these ligands move in closer. But we're going to describe the classic field splitting. Which we'll get to crystal field theory later on in the semester. So the classical field splitting, when we have like a molecule, what it looks like is we have the XY at the very bottom, that's the lowest in energy. Probably should put an energy axis too. We have two degenerate orbitals, the XZ and the YZ. We have the Z squared. We have the X squared minus Y squared d orbitals. So these are all d orbitals again. If you want, you can put that E in there to signify what it is. If not, you can leave it off. Okay. And what we're going to do now is we're going to consider the block functions again at k is equal to 0 and k is equal to pi over a. Oh, we have a sixth person and we have KK. I don't know who that is.
Oh,
Just post this anywhere, huh?
Yeah. I guess someone's really enjoying their band structure lecture. Okay. So we're gonna make a table. We're gonna have actually we'll put orbital. What the block functions look at when k is equal to 0 and when k is equal to pi over a. So let's first consider the dz squared orbital. Okay. Remember the z direction is running this way. We're going to plot the first 3 orbitals there, first 3 orbitals here. Okay. Does anybody remember what the z orbital looked like? dz squared, excuse me. Like if you had to verbally describe it or draw it with your hands, could you show me?
It's a toroid shape. It looks kind of like a px orbital or pz orbital with a donut around the center.
Yep, exactly. So
Damn, Brian.
like that, right? Where there's a center bit that's meant to look like a donut and that's meant to look like a px or pz. Okay, so now when psi is equal to, or excuse me, when k is equal to 0, we're not having a phase change along here, right? So what's the next orbital I should draw? Like how should it look?
Same thing.
Yep, same thing. Well, I've gotten progressively worse as we've gone along. That one's a shitty one. Better. Okay, what about along here? We're starting with this orbital. What's going to happen with at pi over a? We're switching signs, so what's it going to look like?
wouldn't it look the same, but then the outsides will be colored in?
Yep,
Yeah, now we have a vanilla donut instead of a chocolate donut.
yep, delicious. Now I want donuts.
Should have brought some to class for us.
Yikes.
Wait, well, is anybody? No one's in Allegheny. No, Josh is in Allegheny, and John's in Allegheny still. I was gonna say Reed's. They're still pumping out donuts like mad.
Oh yeah.
All the old
Thomas
timers
is better.
touching them and coughing on their hands, though. I don't know.
Boomers.
They would die, not you.
Living the dream, right? All right. So, what type of overlap are we going to have here? Or how many regions of overlap do we have between these two orbitals?
One between each, technically.
Yep, 1. So, what type of overlap is that? Yep, sigma. And is this going to be a sigma bonding or is this going to be an anti-bonding?
Bonding.
Yep. What about this guy?
Anti-bonding.
We get a sigma star for that type. Okay. Let's move to another d orbital. Let's go to the dxy. That one, if we go to draw it out, it's going to be a little tough, but I think we can do it. It's going to be in the plane of the paper. Those look like little DNAs to me for some reason.
Just like chromosomes.
All right, biochemistry.
Yeah.
Hey, I'm not there anymore. Fuck off.
You're free, man. You get to know the cool stuff. And you get a job afterwards.
Roasted. All the biochem students.
They're not here to defend themselves, though. I feel bad.
Anna's gonna pop in. Cheesecake.
Oh yeah, she knows.
I'll bring her in real quick if we need to.
Fucking doctors is saying
She heard us. Oh,
something.
God.
She'd throw her water bottle.
Let us know.
It always, every time it caught me off guard, too. Every single time.
At least you don't have the
As
projector.
soon as she would reach
I
for
was
it, I
just
knew.
thinking that at least you don't have the projector to walk into.
Yeah, exactly. I do miss it, though. I've, like, built up my, I'm getting armor on my thigh every time I hit it.
You could just make a door.
Oh,
Yeah, you have to find something else to crash into now.
Yeah, yeah. I'm
what
gonna
the
start
fuck
smacking
is
it.
going on?
Soon it'll be your baby. You can
That's the best part. See, they're malleable for a little while. They'll go back.
They
together,
bounce.
True, it is true.
right? They don't have bones until like what? They're like 4.
Not even. So much older.
So we
So
have
what?
this d orbital. Remember, there's no sign change, so it's going to look like that. Same nodes. We're trying our best to draw it. We have it. We're trying to draw them like this.
Like as
But
if they would have 4 interactions.
yeah. So there's going to be 4 regions of overlap. What type of bond has 4 regions of overlap? Yep, delta.
Gamma.
And now, is this delta, is it a bonding or is it anti-bonding across here?
Bonding.
It's bonding.
Yep, it's bonding. Now, for the other one, we got to color in the orbitals in the opposite pattern. They're out of phase with one another. What does that mean for this type of orbital?
Sigma star.
Anti-bonding.
Yep, delta star. Okay. 2 down, 3 left to go. Let's do d x squared minus y squared. That one's going to look terrible. We're going to try our best to draw it. The way all of that happens is this dxy shifts about 90 degrees. We're going to have one orbital that comes out, one that goes in, one that's straight up, one that's straight down.
Yikes.
Yeah, I know. What
So
color?
one's like facing us and the other one's up and down.
Yep, like this one is like an X on its side. This one is
Yeah.
like a cross on its side. Sorry, Morgan, Catholic school. All right, and now where should I color this one in? Should it be the same as this guy or should it change? Yeah, same. Okay, and what type of bond is that going to be? How many regions of overlap between these two?
4.
Yep, 4. So what type of bond is it?
Delta.
Yep. Delta. Deltas are getting progressively worse. Is this a bonding or an anti-bonding system?
Bonding.
No. Okay. And we're going to try and draw the same thing. For this other situation. Okay, what's going to happen between these 2 orbitals?
Or a switch.
Yep, switch. And same between these 2 guys. What type of bond is that going to be then?
Delta star.
Yep. Delta anti-bonding. Now the dxz and the dyz, like we said, they're going to be degenerate. So we only have to draw one set there, but know that there's actually 2 sets that we could draw. We got dxz and the yz. And the way they look, they're going to be in the plane of the paper. And they're just in a row. Like that. We can do the same with this one too. Okay. Now, if the first one is got this positive and negative lobe, what's the next one going to look like?
The same.
Yep, the same thing. Third one, same thing, right? Okay. Now, if we color in the first one for the pi over a system, what's going to happen between these two orbitals?
It's gonna switch.
Yep, it's going to switch. So we get that, right? And then what's going to happen with this last one?
It's gonna look the same as the first one.
Yep.
Doctor?
You know it.
Now, what type of overlap do we have? How many regions of overlap between these two orbitals?
4.
2.
Just two.
Just
this time.
2 in this case.
So pi. So that'd be pi
Figuratively.
star.
Yep, this one's going to be pi star. And what's the other one going to be?
Pi.
Pi, yep. So when we go to plot all of these, that's what we want to consider. We want to look at the type of overlap we have. We want to know if we're running from high to low or low to high, and what their dispersion is going to look like. So let's plot the d orbitals.
Why isn't it pi star on the right side?
So on this side,
Yeah.
so this lobe interacts with that lobe, right?
Yeah.
And this lobe is going to interact with that one.
Okay, never mind.
They have the same sign, whereas in this case, they have different signs, right?
Okay.
Make sense?
Yeah.
Cool. Okay. Now, what we're going to do, we're going to plot these guys. Plotting the band structure. We're going to make this a little bit larger. Just because we're going to need the space, and I don't want stuff on top of one another. Except it's too big for the camera. Let's go out a little bit. Okay. Pi over a 0. We got our energy. Okay. Let's think about the different bands we're going to have. We're going to look at their overlap. And we're going to decide if they run up or run down. So we got dz squared. Give me some of the other orbitals that we have, or other bands that we have.
DXY.
dxy, yeah.
EX squared minus Y.
Yep, dx squared minus y squared. Give me other ones.
DXZ DYZ.
Yep. Okay. The overlap. What type of orbital overlap, geez, is the dz going to have?
Bonding and anti-bonding.
That they do have bonding and anti-bonding, but I mean like the symbol.
Constructive.
This
Is that-
one. Let's check that. Yep, sigma. There you go. Okay. And based upon our block functions that we drew, which one's higher in energy? At 0 or at pi over a?
At pi over a.
Pi over a. So is this band going to run up or is it going to run down?
Up.
Yep. Okay, dxy, if we look back at what we did, what type of overlap did that one have?
Gamma.
Delta. Yep.
Delta. What the heck that is.
Yep. And now is that one, looking at the block functions, which one's lower in energy? The 0, k is equal to 0 or k is equal to pi over a case?
0.
So is this going to run up or run down?
Up.
Up, yep. X squared minus y squared. What type of overlap did we say that's going to have?
Still delta.
Yep. Is it going to run up or down? Yep, up. dxz and dyz, they're both the same. What type of overlap do they have?
Pi and it's gonna run
Pi
down.
star.
Yep. They have pi overlap. And are they going to run up or are they going to run down? Josh, you said pi star, which is.
Well, yeah, so it's running down, but it's a pi overlap. Yeah.
Yep. Going down, son. All right. Now, what we want to keep in mind is we want to keep in mind the splitting pattern that we had. These tell us our energetics a little bit. The highest in energy case is going to be this dx squared minus y squared. That one's going to be the highest energy. But we have to consider as these things run into one another. So which band will have the greatest band dispersion? Meaning which one's going to have the highest difference between the top and the bottom?
DZ.
DXY.
Oh, just kidding.
Oh, I'm sorry. No, DZ squared will have the highest dispersion, right?
That's what I said.
Yep, you were right, Tara. Sorry, you should have been. I knew what I was doing.
Is that just due to its sigma overlap?
Yes.
Oh, okay.
Okay. What's going to come next in energy? What did we say for the molecular system? We had these guys, right?
Right.
Okay, what type of overlap did these ones have?
Pi.
Pi. So their dispersion is going to be a bit less, right? So we can't start as high. Drop down a little bit. And this is the dxy, dyz. Oh, I'm sorry, this is xz. And that's the dyz. And since they're degenerate, they're overlapping with one another, right?
Right.
Okay, then we'll have the dxy. And we said the dxy has delta overlap. Since it has delta overlap, its dispersion is much weaker. We have dxy. And then what's the last orbital we've neglected so far?
Dx squared minus y squared.
Yep. And it's going to have a dispersion like that. Okay. Now, if we were to look at the center of each of these bands, we're gonna you don't have to draw this in, but I just want you to keep this in mind. So we're going to cut the center of them. So we're looking at the center. I've drawn this one twice, but that's, if you count and look at where the center of these bands are, they should line up approximately with this molecular orbital diagram. Okay. Cool. So are there any questions about that?
How would we be?
We have to draw that on the test.
Yeah, you will. Your next classroom assignment is actually looking at a metal that that has some electrons in it. Now,
So would we be told the d orbitals that exist, or we would have to figure that out?
no, you would have to know the d orbitals. So
And how would we know the d orbitals? Like on a
oh,
block
like how would we know this pattern?
No, I mean, like, how would we know that, like, oh, that has a dx, y, or
Oh,
like,
if it has d orbitals, it has all of these, right?
Oh.
Yep. So if you think of, like, if you have an n is equal to 3, if going back to quantum numbers, what are the possible values of L we could have?
Oh,
-3,
2, 1,
-2.
0.
Yep. And so anything that has an L value of 2, that has to have d orbitals. And you don't just have one, you have all of them.
Okay, so these are the 5 possibilities for d orbitals.
Yes.
Okay.
Yep. Okay, but we forgot one thing so far. We said we had a D8 metal. How many d electrons do we have then? Not really a trick question.
5?
No, 8.
8.
Probably 8.
Yeah, we have 8
Alright.
electrons that we got to fill. Okay, so we got to think of where to put this Fermi level. Okay. So, anybody have an idea of where it should go?
Well, I'm assuming there's probably 10 electrons total from the
Yep.
orbitals given. So we need to do it somewhere between the 8th and the 10th orbital, like electron wise. So between the top and the lower 2.
Yep, so you're saying between these two guys, right?
Yeah.
Yep, that's exactly right.
Doctor?
That's where the Fermi level is. If the Fermi level is, if you might have said, hey, why isn't it just right on top here? As soon as you fill a band completely, it goes in between 2 different bands. Because you have to be at the 0 of what's called chemical potential. However, if we were bisecting a band somewhere along in here, the Fermi level would still cut that band in half, or cut it at some point. Does that make sense?
Mhm.
Yeah? Okay. Everybody good? Okay. Let's move on to, let's see. We'll do 2D systems, and then we'll talk about DOS. How much time do we got left, though?
15 minutes.
15 minutes? Okay. Yeah, let's plot in more dimensions, because right now we're only dealing with 1 dimension. Let's go to 2 dimensions. Am I okay to move this out of the way?
Yeah.
Okay. So let's ask, what about more dimensions? So for this, we're going to drop back. We're going to drop back to the hydrogen chain, except we're going to do it in a 2D crystal.
So the one we just did before was 1D?
Yep, that was 1D. Let's assume we have a 2D crystal lattice of H atoms. And they're evenly spaced around. So we're going to have AX is equal to AY. We only have to talk about one lattice constant here. And the way this looks, we're going to try and draw a grid. And this is our unit cell. And at each of these points, we have an H atom. And our coordinate axis, X is going to be in this direction, Y is going to be in this direction. And this would be AX, this would be AY. So the lattice vector between those. We'll try to draw that. Does that plot make sense to people?
Yes.
Okay. But now, just like with a 2D particle in a box, we now have 2 lattice vectors, and that means we have 2 K vectors. So we have two lattice vectors. That means we have two k vectors. So we're going to have kx, we're going to have ky. So let's draw the block functions for the following systems. Let's draw the block functions. The first one we're going to do, we're going to have kx is equal to 0, ky is equal to 0. Okay. And remember, this is going to be almost just like the 1D chain again, with y along here, x along here. When we looked at the 1D hydrogen chain and k was equal to 0, did the sign change between these functions
No.
as we went along? Sorry, everybody's scrambling down. Oh, wait a minute. All right, so when
Didn't change.
didn't change, right? So k is equal to 0 in both the x and the y direction. Do I need to fill any in or show a phase change? Nope. So this is all bonding. Let's look at an example when kx is equal to pi over a and ky is equal to pi over a. I drew those too close together. Oh well. Be okay. All right. Let's consider kx first. Across this way, what should happen to this block function?
Like the middle should be filled in.
I'm sorry, what was that?
Like the middle should be filled in, and the two outsides will stay the same.
Yep, so that one should be filled in, right? Now let's consider the y direction for this first column. Same thing should happen, right? Okay, what about this column?
The top one,
Yep. And this guy?
the middle.
No.
Yep. So this one is a completely bonding orbital, right? What about this guy?
Anti-bonding.
Yep. It's a completely anti-bonding system. Now let's consider a couple more. Let's do when kx is equal to pi over a and when ky is equal to 0. What's that going to look like? What's going to change in the x direction?
Nothing.
Nothing in the x direction with pi over a?
Well, I don't think anything's going to change. If it's the same as the one. on the
Colored
left.
in.
I mean, like it won't change compared to the second.
I see what you're saying, Josh. So this is going to be colored in, right? What about for this direction? Is it going to be in phase or out of phase?
In.
In phase, yep, because ky is equal to 0. So across x, it should all be out of phase. So what else do I need to do here?
Color the middle
Fill
top.
in the middle.
Yeah. There you go. So this is anti-bonding only in which direction?
X. Or not, though. Yeah, well, yeah, the X.
Yep. But it's bonding in Y. Okay. Now, if we consider the opposite, we do, yeah, I'm focused on. We do kx is equal to 0, ky is equal to pi over a. How should that one look?
The
Well,
opposite.
then put the 3 in the middle for the second row is filled.
Mhm. Yeah, so Maddie, Josh, you're right. It should look the opposite. Should be colored in that way, right?
I
So
heard Maddie
it's-
first, but
Pardon? What'd you say?
Tyler got it.
Did you
I
say
didn't
Maddie said it first?
Yeah, well, it's because he said Maddie first, too.
I didn't hear. You want to say it out of the screen?
I
Tough
was,
guy. He's learning.
I was supporting you.
Keep talking
Oh,
smack.
gosh.
You got it. You
That's how it always goes, right? Big talk over the internet.
Yeah.
Don't worry, I'm the same way. Okay, so it's bonding in which direction then?
X.
X.
Yep. Anti-bonding in which direction?
Y.
Okay,
Ooh.
now let's look at a situation we haven't really quite considered yet. Let's say we're going to look at kx is equal to pi over 2a. Ky is equal to 0. Okay. I forgot another. There we go. Ky, let's consider that one first. What should happen along there? Should they all be in phase or out of phase with one another?
Won't they all be in phase?
Yep, they're all in phase with one another. Kx, we're at a situation where it's pi divided by 2a. So let's look at our band structure real quick for our 1D system. This is our 1D system. So we're at pi over 2a. Where on that plot is this?
Right,
Yep, right in the middle.
that's a Fermi level.
Yeah, right where that Fermi level actually is. Okay, so what do the block functions look like at that point? Or we said that these guys are bonding, right? What about these guys?
The
Anti-bonding.
bonding.
So what about here?
Non-bonding.
Non-bonding. So really they have no contribution. So what should we draw on this plot? If they're non-bonding,
All black.
all black?
Like alternating.
It would
Yeah.
be nothing, right? Because there's no contribution at all.
Yep, there's no contribution at all. So there's nothing there.
I already drew all my circles. Great.
Sorry. What about over here?
There
Is
was
there-
zero there.
What's that?
No, never mind.
Nothing.
What?
When you say it like that.
Nope, not like this.
Black.
They're actually all going to be, sorry, loud phone. Tell me I need to shut up soon. These are all going to be colored in because they're all in phase with one.
I use
Okay.
chemical intuition.
Yeah, we're building intuition right now. Okay. We don't have enough time to really talk about what the Brilliant zone and the band structure of this look like, so we'll do that next time. I am going to post 2 classroom assignments for you guys to check out and to look at. But are there any questions that you have for any of the information we covered?
I don't know. I think I'll be good.
Okay.
Yeah. I mean, we don't have a test on this tomorrow, so
That's
Yeah.
a fair point. That is
a little more concerned.
We got time. All right, well, cool.